Hello. Today we're going to be talking about advanced curve sketching. This is curve sketching using calculus techniques. As this says, we've used a pre-calculus curve sketching recipe in Unit 1. So now we want to incorporate the additional calculus techniques we've learned recently. So we're going to go quickly through the Unit 1 techniques. These should all be familiar to you both from last year, your work last year, as well as from Unit 1. The last two steps, finding increasing, decreasing behavior using an f prime number line, and finding concavity using points of inflection, and f double prime number line, that's the new stuff that we've learned in Chapter 4. So in Lesson 4-4, we're going to be doing a lot of the same stuff with two new techniques, and that all comes from the previous two lessons. So make sure you've mastered 4-2 and 4-3 before this point. Here we go. So in a lot of cases, they will give you the first and second derivatives as well as the original function. If this is not given to you, you must derive them first. And please work carefully as you do that. On a test, they would most likely be given to you because if you cannot get those, you have no hope of getting any points for the last three things. F has no domain restrictions. The denominator of f is always positive, so we're hunky-dory. That means we have no vertical asymptotes. That means we have no holes because there's no kinds of discontinuities. X-intercepts. We're talking about using the equation f of x equals 0, which would be 2x cubed equals 0. Because for a fraction equals 0, the top has to equal 0. So only at x equals 0. And remember to list your x-intercepts as points. A clever student would notice that this is also our y-intercept. We're going to graph that right now. If you didn't notice it, y-intercept, just to review, is f of 0, but we already did that. I don't know why it's writing on everything. Okay. I also want to mention that this is an odd x-intercept. Now, this will become easier to tell now that we have additional calculus techniques, but it's an odd x-intercept because the power of that root is odd. That means we will cross through that x-intercept. End behavior. I'm going to do end behavior in blue down here. We're drifting. We're drifting a bit. End behavior in blue. We're talking about the highest power on the top and the highest power on the bottom. So it's going to be like 2x, which is a line with one end up and one end down. And you can go ahead and put those on if you're following the ideas we used in Chapter 1. It was helpful to know that eventually we're going to go up and out. But again, this is going to become much more clear in a minute. The symmetry we have here is origin symmetry. You can think through that. If I plug in a negative value, -1, I would get negative f of -1 is -1, and f of +1 is +1. It's not really important. If you need help with that, you can come and talk to me. for relative maxes and mins, now we're finally going to be talking about f prime. So the critical numbers here, the critical numbers of f are the zeros and the discontinuities or the domain issues of f prime. You should notice that the only critical number here is x equals 0. That's the only number that could make f prime equal to 0. And there is no numbers that can make f prime undefined. Going really quickly over that, if you need help with that, you should watch videos 4-1 and the videos for 4-2. So, before 0, we're talking about a value like -1. I would expect most of you to be able to see that this denominator must be positive. This part of the numerator must be positive, and this part must be positive. So in fact, there are no possible sign changes. Because we are increasing, we have increasing behavior on either side of f prime, we will draw one guideline, always increasing. Since there's one guideline always increasing, we have no relative max and no relative min. Finally, our points of inflection, I suppose I'll use this lighter color, f double prime number line, our possible points of inflection, and here we have a much more varied situation. Our possible points of inflection, we notice the bottom will never equal 0, so there's no places where f double prime will be undefined. The top has 3 zeros, specifically 0, root 3, and -√3. Please go carefully, make sure you calculate your possible points of inflection very carefully. You do not want to lose points just because you messed that up. Put them all on the number line. And now we're going to test the sign of f double prime around those points. Something less than -√3 would be something like -2. If you're uncomfortable with plugging things in for everything, you should be aware that the bottom is always going to be positive. It's a positive number cubed. -2 in the top would make this positive and would make that positive. So we have a positive concavity. Concave upward. Between 0 and -√3, we're talking about -1, positive, negative. Between 0 and 1, negative and negative. And after positive √3, I don't know why I wrote -√3, we have something like +2, where we have negative and positive. So we have a negative. So we see this switching of concavity at each of these points. Now, PI is standing for points of inflection. They are asking me to write both the y and x coordinates. So I will mention that I have a -√3. And if you carefully plug this in, you would get -3√3 over 2. Yes. Positive √3, this is actually an odd function. And that's one reason to calculate whether it's an odd or even function, whether it has origin symmetry or not. It'll help you calculate this stuff really quickly. And we actually know the last point of inflection is at the origin because we already calculated what happens when you plug in 0 to the original function. So one thing I like to do is to combine these number lines, and for this you kind of want them lined up. So we're going to be talking about concave up and increasing, and that's going to switch at positive root 3, then concave down and increasing, which switches at positive 0, not positive 0, concave up again, followed by concave down again. And you can kind of see how this provides me a really good idea of what this function will look like. So let's go ahead and graph our other 2 points of inflection before we forget. Root 3 is some number between 1 and 2. It's actually closer to 2. 3 root 3 over 2 is close to 3.5. It's going to mess up my arrow. That's one reason not to do arrows this early. Negative 3 root 3 over 2. Similar situation. Here we go. So starting from the end behavior. So I'm going to actually move my end behavior because those points are way too close to the boundary. This is what kind of live adjustment you want to be able to do. So starting from my end behavior, I have a concave up situation, and I'm increasing until I get there. And now we're going to switch to concave down and increasing. You don't have to make this look drastic. A lot of people feel like they need to show me going down, but that would be concave down and decreasing toward the end there. So we're going to be very careful that we're going to be concave down and increasing until we get to the origin. Now here I kind of crossed the origin. I'm going to adjust that because I don't want to lose points on my test. Bam. Possibly a flattening out to reflect that the slope here is 0. The slope of f is 0 because f prime is 0 at that point. Definitely want to show an inflection. So see how this is clearly concave up and that's clearly concave down. Now switching to concave up again. And again, don't be too drastic. And now concave down. That's a little bit too much of a sharp turn for me, huh? And that's it. I will now, when I grade your test, be checking that your concavity matches, be checking that you always made an increasing function, something that's always increasing. And that's enough for this one. Next, another rational function. Now, here they did not factor this for me, at least not the first one. These other functions may give you hints, but importantly, you want to factor it on the test day. You want to make sure everything is factored just like you would want. So now we clearly see the roots of the bottom. The bottom's roots, the things that would make, the x values that make the denominator 0 are exactly our domain restriction. So x cannot equal 1. I check to see if f can be reduced. It cannot. That means the domain restriction is in fact a vertical asymptote. Notice how this one says not equal and this one says equal. I'm going to go ahead and draw that on here now. There are no holes. All the domain restrictions were vertical asymptotes. X-intercepts. What would make the top 0? That would just be the point 2/3, comma 0. Please be careful to write this as a coordinate. The power of that factor is odd, so I know I will go through this point. 2/3, comma 0 is very close to the asymptote, somewhat surprisingly close, but we're sure we're doing it right, so we don't question it. F of 0. When you plug in 0 to this function, It's especially easy to use the factored version. We get negative 2 over 1. So that would be the point 0, comma, negative 2. On previous tests, I've seen people check whether that's odd or even. We usually do not talk about y-intercepts being odd or even. It doesn't really have a good meaning. Zero, comma, negative 2. Right there. Sorry if I had to make it a giant. I just remembered we didn't check if the vertical asymptote was odd or even. The power on that factor is even. The end behavior for a function like this is y equals 0, a horizontal asymptote. We're talking about 3x over x squared. The power on the bottom is bigger, so y equals 0. Symmetry, none. This guy does not have any symmetry. Every year there's always someone who writes yes here when it does have symmetry. That is not marked correct. It makes me chuckle, but it's not marked correct. This is all pre-calculus stuff. This should all be familiar to you by now. If it's not, you need to come in for extra help. Nothing wrong with that. What's wrong with it is you know you need it and you don't do anything. Critical numbers. We're talking about x equals 1/3 and x equals 1. 1 would make f prime undefined. 1/3 would make f prime 0. I note that it's an f prime number line. Help me out. I'll put 1/3 here, 1 over here. Because 1 is a place where f is undefined as well, it's not a critical number. It's a domain restriction of f. It's still important to check, and that 1's really bleeding in there. There we go. Before 1/3, we're trying a value like 0. 0 in the top makes positive. 0 in the bottom, negative cubed, negative. Positive over negative, negative. Between 1/3 and 1, this is probably the trickiest it gets, 2/3 is probably the smartest thing you could pick. Yes, you could pick 1/2, but 2/3 is going to multiply nicer with 3, the negative 3. If you pick 1/2, I'll do it the hard way. Through negative 3/2 plus 1 is still negative. 1/2 minus 1 is negative. We get positive. If you're smarter to use 2/3, we clearly get a negative 2 out of that. Negative 2 plus 1 is much more easy to see that that's negative. 2/3 minus 1, it's easy to see that that's negative, so on and so forth. After 1, a value like 2, the top is negative, the bottom is positive. Yes, so we have a negative. So that means our guidelines will be something like a decrease, followed by an increase, break, followed by a decrease. Do not make it a drawing that makes it look like we have a max here, because we don't, because it's a domain restriction. So there's still no relative maximum, but there is a relative minimum at 1/3, comma, and now where do I get these y values from? I get them from f. F of 1/3, 3 times 1/3, 1. 1 minus 2, negative 1. Divided by 4/9, we're talking about negative 9/4. And you want to be very careful that you do that math correctly. More careful than I'm being in this video. But you have all the time in the world right now to go write down and see how I got that. 1/3 is going to be closer to 0. And negative 9/4 is slightly further down than 2. It's okay if we exaggerate it a bit. Now I'm going to erase this little work for the horizontal asymptote. I'm going to slide this up. Like I said, we're going to want to make sure we've aligned everything. The possible points of inflection are actually x equals 0 because f double prime would be 0. We should worry about 1, except 1 again is a domain restriction. So I'm going to use the fact that I need to have everything lined up. There's 1. I want my 1's lined up. The domain restrictions of f should be on my f double prime number line. I do not want the critical numbers on here, but I want to keep everything in the same relative order. So I'm going to put 0 to the left of 1/3. I want 1/3 between 0 and 1. I want my 1's lined up exactly. That'll help us for curve sketching a lot. Now, before 0, f double prime. We should notice that anything to the 4th power will be positive. Negative 1 is the test value. So it's negative over positive, negative. Between 0 and 1, we're talking about 1/2. 1/2 is positive in the top. Positive over positive, positive. After 2. After 1 is like 2. 12, positive over positive. So we go from concave down to concave up to concave down. I'm sorry, from concave down to concave up to concave up. Positive f double prime means concave up for f. Be very careful. Yikes. So 0 is a point of inflection. Luckily for us, we've already calculated its y coordinate by using f. It's the y-intercept. Okay, right there. Combining these two, we're talking about a concave down behavior until we get to 0. Okay, I kind of did what some students do. I don't think I really would notice it. What you don't want to do is this. That's concave down and increasing. What does this say? Decreasing. Don't emphasize the concave down. Just start decreasing with a concave down shape until you get to 0. Right above where we are. After 0, we will be concave up and decreasing. That's a really wide bowl. At 1/3, we switch to being increasing. We are still concave up. So we actually will get a nice concave up shape. Ugly though it looks like right now. Concave down, decreasing, concave up, decreasing, concave up, increasing. Again, concave up does not mean increasing. Concave down does not mean decreasing. Common mistakes. Concave up and decreasing on the other side. Look how that matches the fact that I know I have an even asymptote. So now it's about transporting this sketch over here. So I have a asymptote, a horizontal asymptote. That's my M behavior. We're going to start over here. We know there's no x-intercept, so don't start above. Starting down here. We are going to be concave down and decreasing all the way until 0. And that's why I'm going to be really careful about how I draw this. I will be forgiving. Concave down, decreasing. We switch to concave up and decreasing. Bump. Concave up and increasing. Do your best to hit that point. All right, I'll try again. going to be incredibly steep. But we're trying to show a concave up shape. It's okay if you can't quite get it. Concave up and decreasing. Down to the asymptote. I'll be forgiving about little bumps you have. So again, a lot of this work can be done without calculus. All of this is pre-calc skills. Whereas these three are calc skills. We're going to be much more interested in whether you can do the calc things than the pre-calc things. It's all worth points. Again, with all this information, it's really hard to draw an inaccurate sketch if you're doing everything you're supposed to be doing. Practice, practice, practice. Last, a radical function. Again, all this stuff is given. Radical functions, you always want to be aware of weird end behavior, ladies and gentlemen. Here we go. Domain restrictions. None. This guy is wonderful. There's no way to get a negative inside this radical. There's no way to get a 0 inside this radical. So there's no way to get a 0 in the bottom. All reals. So that means no vertical asymptotes, no holes. X-intercept. The only way to get a 0 out of this fraction is if the top were 0. And if the top were 0, we'd have 0, 0. So we know the origin is in the mix. End behavior here. This is like, and again, if you didn't understand this in chapter 1, you didn't understand this in chapter 2, you got to be careful. This is like y equals x over absolute value of x. Your second chance to understand. So we have a right horizontal asymptote. When we're far to the right, a big giant positive number, positive 100 over positive 100. A right horizontal asymptote at y equals 1. And a left horizontal asymptote, notice how the bottom's always positive, negative 100 over positive 100. Y equals negative 1. The faster you can make that decision, the better this whole question will go for you. I just want to shrink my... Perfect. Well, whatever. We'll just hope that's enough space to do everything else. So that's the end behavior. We're talking about way out here. We approach this. So I'm trying to avoid drawing it like this because many students start to assume you can't cross it. You can cross horizontal asymptotes infinitely many times. So if it helps you, draw them way out here like this. The symmetry in this graph will also be origin symmetry. This graph, this function also has odd property, where if we plug in 1, we get 1 over root 3. We plug in negative 1, we get negative 1 over root 3. All right. Critical numbers. I'm going to write them right here. The critical numbers. Is there any way to make the top of this function equal 0? Nope. Is there any way to make the bottom of this fraction 0? Nope. There's no critical numbers. That automatically means there's not going to be any relative maxes or mins. It also means my f prime number line will not have any tick marks. I get to check any value I want. What's the easiest value in the world to check? 0. F prime will always be positive. Again, you can check that by plugging in 0 into f prime, positive over positive, or you could realize that this denominator will always be positive. So in fact, that means in terms of our guidelines, f prime will always be increasing. Sorry, f will always be increasing because f prime is always positive. Possible points of inflection. What kind of values can make f double prime equal to 0? We set the top equal to 0, and we notice that x equals 0 is the only possible value. What kind of numbers can make the bottom equal to 0? Nothing. We make an f double prime number line. There's nothing to line up with up here, so I'm just going to put 0 in the middle. Before 0, -1. The bottom will always be positive here. X squared plus 2 is always positive. So everything is always positive. -1 in the top would make a positive, positive over positive. +1 in the top would make a negative. Negative divided by a positive is negative. So we're talking about a concave up, happy face, to a concave down, sad face. That means 0 is an actual point of inflection. And we already know its y-coordinate. Again, the y-coordinates will always be given by f. We're graphing f, so the y-coordinates are f. So we're talking about concave up and increasing, switching to concave down and increasing. An S-type shape. And that S-type shape fits really nicely in here. You should see that. There's no other special points to plot. So I'm making a nice curvy shape going through the origin. A nice curvy shape. Done. In previous chapters, we were talking about how we don't know that it does this. I can't cross the axis. We don't know that it does this. Now we do, because that would be lots of relative maxes. It's smooth. It's increasing. Don't show me this kind of behavior to show me it's concave up. That would cross the x-axis. That would give me another x-intercept. I'd mark you off for that. This shows me that it's decreasing. It's never decreasing. I don't want to see fake behavior. Just draw me things that fit all of the data. Be very careful. Everything in 4-4 is available to you. I would highly recommend doing a bunch of examples right now. Come back to this video if you need help. Ask me in person if you need help. Good luck. Have fun. I'll talk to you later. Bye for now.